Early 2026. This was not a regular test. It was an unexpected and critical step in Starship's evolution. SpaceX's Starbase team prepped Starship Flight 12 for what was supposed to be a routine test, until, without warning, engineers authorized a full-scale cryogenic stress procedure never attempted at this point in flight readiness. Block 3 hardware was placed under maximum pressure, new materials were pushed to their physical limits, and the whole aerospace community was left guessing about what SpaceX was risking, and why now. The answer lies inside a test sequence that could redefine how quickly humanity reaches Mars, if everything doesn't go sideways first. Valve actuators snap open, and the first rivulets of supercooled liquid oxygen begin to flow into the lower tanks. Within seconds, a white frost creeps across the stainless steel barrel, tracing the path of the cryogenic fill as temperatures inside plummet. The methane lines follow, each quick disconnect arm sealing tight, pushing chilled propellant through insulated pipes at a controlled rate. Engineers monitor the fill profile, ramping pressure with precision. Too fast, and the metal contracts unevenly, risking microfractures. Too slow, and the test loses its value. As the tanks approach target levels, a low rumble signals the engagement of the structural test stand's thrust rams. Hydraulic pistons press upward against the booster's base, simulating the force of 33 Raptor engines at full throttle. Pressure sensors confirm the tanks are holding above operational limits, while the rams drive loads through the airframe that match and even exceed the stresses of actual flight. The test sequence calls for a series of holds and ramps, force applied, released, then reapplied. Each cycle is designed to reveal any weakness in welds, joints, or new material overlays unique to Block 3. Frost thickens, vent valves hiss as excess pressure is bled away, and the booster's skin creaks under the shifting balance of thermal contraction and mechanical strain. The entire procedure unfolds in a tightly choreographed order: fill, chill, load, hold. Every step is timed to the second, each pressure surge and temperature drop logged in real time. On this night, the margin for error is measured in fractions of a degree and millisecond spikes in force. The physical test has begun. Now it is up to the sensors to capture what the human eye cannot see. Rows of sensors stitched along the booster's skin record every twitch and tremor as the test progresses. Strain gauges wired in tight grids across weld seams and barrel sections feed microvolt signals to data acquisition units mounted just beyond the frost line. Each gauge samples the steel's deformation thousands of times per second, translating invisible stretches into a digital heartbeat. Pressure transducers in the liquid oxygen and methane tanks track the rise and fall of internal forces, mapping the pulse of each thrust ram cycle. Thermocouples log the temperature drop as super-cold propellants soak the metal, watching for sudden spikes that might warn of brittle fracture. All this data streams through fiber bundles to the engineering console in real time. On the main screen, traces race from left to right, lines for tank pressure, colored bands for strain, and sharp drops or surges that stand out like warning flares. The console overlays these traces against a predicted envelope, a shaded region that defines the safe zone for each parameter as the test unfolds. If a strain gauge reading creeps past the edge of this envelope, the software highlights it instantly and flags engineers to watch for trouble. A structural test engineer, eyes fixed on the live plots, describes the rhythm of the strain time curve as a kind of music, steady and predictable, with no jarring notes. The goal is not a perfect flat line, but to recognize the subtle expected shifts that signal the structure is flexing as designed. When the envelope holds and the traces stay contained, it means the booster's skin and welds are withstanding the punishment. Every spike and every dip tells a story that only the sensors can reveal. A split-second failure can erase months of progress. That reality hit hard when Booster 18 suffered a catastrophic rupture during an ambient gas pressure test at Massey's site in November. The culprit was a composite overwrapped pressure vessel, COPV, hidden inside the chine that failed without warning. The resulting cascade ripped a gaping hole in the liquid oxygen tank. No engines or propellant were loaded, but the damage was total. SpaceX teams moved quickly, cutting away the damaged methane tank and securing the remains by crane. Booster 18 was written off within hours. The aftermath forced a reckoning. With Flight 12's schedule already tight, the loss of a Block 3 test article threatened to stall the entire campaign. The pressure was not just technical, it was environmental. Starbase's new cadence demanded rapid recovery and proof that Block 3 could withstand the rigors of repeated use. The risk was tangible. Another failure could set back the Mars roadmap by months, if not longer. Pad 2 became the focal point for recovery and readiness. Crews installed the upgraded quick disconnect arm, integrating fluid connections and new methane hardware to support the next round of tests. The hold-down arm's protective doors were cycled and locked, verifying their strength against the violence of a full static fire. Meanwhile, Booster 19's build moved at record speed, just 5 weeks from start to rollout, demonstrating SpaceX's intent to push through setbacks, not pause for them. A flight test lead summed up the mood. We don't have the luxury of waiting for perfect conditions. Every test is a calculated risk, but standing still is the biggest risk of all. Inside the control room, tension settles over every workstation. The last data sweep flashes green, but the memory of Booster 18's rupture lingers. Engineers weigh the numbers against the risk. One more hold could mean days lost, but a premature push risks another catastrophic failure. The telemetry overlays pulse with live traces, pressure, strain, actuator force, each line dancing within a shaded envelope that defines the razor-thin margin between success and disaster. Launch operations. Lead's voice cuts through the chatter. The lead says, "All stations, this is the final call." Block 3 envelope is holding. No out-of-family readings. Tank pressure stable at 125% of flight maximum. The strain grid shows within 0.3% of the model. Actuator force nominal. Confirm go or no go. One by one, consoles respond. Propulsion, structures, guidance, all report OK. The risk calculus is clear. The odds of a repeat failure have been driven down by 12 rounds of cryogenic proofing. But the consequences of a missed anomaly are absolute. A single click echoes as the lead arms the sequence. The overlay, composite, pressure, strain, actuator becomes the verdict. If any trace crosses the envelope, the system will halt the test in milliseconds. If not, Flight 12's Block 3 hardware will clear the most punishing trial SpaceX has ever attempted on the ground. The decision is locked. The countdown resumes. Every eye tracks the telemetry, knowing the next few seconds will decide whether Starship's new era advances or stalls on the pad. The engineering console locks onto a single frame, 3 data channels layered into one composite overlay. Pressure, strain, and actuator force, each rendered in its own color, trace the live heartbeat of Block 3's trial. The graph's background glows with a translucent envelope. a boundary calculated from months of finite element modeling and previous test runs. Every data point pulses against this digital silhouette. The pressure trace arcs upward, holding steady near the upper margin. Strain readings undulate, echoing the booster's flex. Actuator force plots ripple in sync with each ramp of the thrust rams. No commentary, no verdict, just the raw convergence of numbers and models. For a moment, the overlay sits frozen, inviting every eye in the room to search for the smallest deviation, the hint of a spike, the signature of a system pushed to its absolute edge. Success and failure in a test like this are written in the shape and timing of the data itself. A passing sequence means every trace, pressure, strain, actuator force remains inside the shaded envelope, never crossing the digital edge set by months of modeling and prior tests. For Block 3, that means tank pressure holds steady at 125% of the highest flight load for the full duration, with strain readings never deviating more than 0.3% from the expected curve. The actuator force must match the commanded profile within a narrow 5% margin. Any sudden drop in pressure, a runaway spike in strain, or actuator force that lags or overshoots its target is a red flag. The system is programmed to halt the moment a trace crosses the threshold. No second chances, no overrides. This pass-fail logic turns raw telemetry into a verdict. Either the structure bends, flexes, and recovers as designed, or it reveals a weakness that cannot be ignored. On this night, the difference between a green light and a hard stop is measured in fractions, a margin that separates progress from another lost booster. Right now, Starship's new test data is rewriting what's possible in rapid, reusable spaceflight. As engineers push hardware past old boundaries, the next generation of missions draws closer. Every unexpected trial accelerates the path to Mars and turns today's experiment into tomorrow's giant leap. Thanks for watching.